All right. All right, some fun here with the displays. So I will try to not instinctively point this way to the slides, but point this way instead. Today we're talking about probabilistic modeling. And actually, I would say that probably of the lectures in this course, this is going to be one of the maybe most challenging. We'll see. I'll see what you guys think. I mean, it isn't the most mathematically detailed, but we're going to cover a lot of stuff that where we don't really cover all the details. So my guess is that some of the concepts might be particularly kind of amorphous if you haven't seen them before. And if you have, then hopefully this will reinforce some of the things you've seen before. But if you haven't seen them, hopefully this will give you some intuition of what you can do with these techniques from a data science perspective. So some quick announcements first. I think it's actually, I'm going to create a Piazza post on both these things. I just decided these two things just now. So first of all, homework 5, as probably a lot of people know, there was a bug in the autograder where essentially, it's the worst kind of bug too. It's the kind of bug where you got credit and then it was for anything answer, and then it was fixed, and then you no longer got credit. So it's much worse to have the other kind of bugs, it's much better to have the other kind of bug where you don't get credit and then you get credit. This kind of bug's very bad, and so we apologize for that. Hopefully you don't hold it against us too much, but we're going to extend the deadline one day for that, so it's going to be due on Friday instead of Thursday. It was already to Thursday because we released it a day late, but it's going to be Friday. The other big thing is that for homework 6, you're starting to have a lot of stuff going on. I know this was a comment some people had. You have your final project due. You're going to have other finals in other classes, I'm sure. And now we're also at the point where we're kind of picking and sampling from different topics in the lecture. So what we're going to do is we're going to have homework 6 is going to be released on Friday because the homework's due Friday. You'll have 2 weeks. It'll be due the following Friday. But it'll be kind of a best sum out of 3 for the homework. So 388 students will have to only complete 1. Instead of normal 2 out of 3, you'll have to complete 1 out of 3. You can actually pick whichever ones you want out of the 3 to do. 688 can do 2 out of 3, either 2 out of 3. And then if you want to do more than that, it can count for extra credit. You'll get half the points. So after you hit the threshold, you'll get half that many more points, however many more points you have. And so you actually can submit, partial credit for all of them. And for the 688. Sorry, for 388, whatever you get above 2/3, so whatever you get above 1/3, you get half the points for that, and then 688, whatever you get above 66%, you get half the points for that. So hopefully that'll also let people make up a little bit of points if you're sort of worried about anything, but it's only half points and it's one homework, so don't worry too much. The goal is to give you the chance to pick one subset of problems to work on as opposed to all of them. Okay. So I'm going to talk today about probabilistic modeling. And we're going to cover a couple things. And actually, we're going to have to cover it at a pretty high level because there really are entire courses on this exact topic. And so I don't want to spend too much time doing on any one aspect of this. But I want to highlight some basic ideas of probabilistic models and probabilistic inference, including, for the first time in the course, Bayesian statistics and Bayesian modeling. So largely we've been focusing on, though we haven't used those terms, we've been largely focusing on what's called frequentist statistics so far in this course. And I want to give a little bit of perspective on other possible ways you can think about modeling and fitting models to data. And then finally, I'll talk about probabilistic programming at the very end. And I'll describe what that means in a second, but basically these are ways of writing short programs that encode probabilistic models and then automatically performing inference. So chances are, from a data science perspective, if you want to use probabilistic models and maybe you don't have too much data, you should probably be using these probabilistic programming languages and not trying to write these things from scratch because some of the more complex inference techniques get very, very complicated. So let's start off by talking about what probabilistic graphical models are. And these go by a lot of names. So you may have heard the names probabilistic graphical models. You may have heard the names generative models. You may have heard the names Bayesian networks. And there are subtle differences between all those things. Some are more general than others. But I'm going to more or less use all of those things synonymously for this lecture at least. And what these things are all about is they're really just about representing distributions P of x. So if I have some random variables, and I want to specify some distribution over these random variables, in general, that could be very complex when you start talking about a high-dimensional set of variables here, right? So if I have a binary random variable set, these things just take on values 0 or 1, and I have n of them. So x is an n-dimensional binary random vector. And that's what that notation means there. X is going to be 0 or 1 to the n, meaning it has n dimensions, each of which is 0 or 1. Then if I want to specify a distribution over all those possibilities, I need to specify 2 to the n minus 1 different numbers, different parameters for my distribution, right? Because I have to say what's the probability of every single possible assignment. The minus 1 there comes from the fact that because they have to add to 1, you can leave off 1 probability and you're OK. But basically, I have to say, what's the probability that x1 equals 0, x2 equals 1, x3 equals 0, etc. I have to specify all of those things for every possible value of x that x can take on. And there's no other way of doing that. If for a general distribution, you just have to specify all those things. You can't get around that. And quickly, of course, that will not scale, let alone when you start talking about things like continuous distributions, right? Maybe that aren't, say, Gaussian. How do you go about representing those things? And so these are typically very hard to do. And what graphical models do is they offer a way to represent distributions. I shouldn't quite say these same distributions because they aren't quite the same thing, but to represent distributions much more compactly by exploiting conditional independence of the random variables. So it turns out that in most, well, maybe not, I don't know if I want to say that this is true in the real world or not, but oftentimes you will come across distributions where even though the distribution is over a high-dimensional object, you don't need to encode a full joint distribution over every single possibility here, right? Maybe they're independent, all the variables, in which case you only need to specify n different numbers, right? Just the probability of each one. Maybe they aren't fully independent, but there's some conditional independence that lets you still specify the same distribution much more compactly. And that's kind of the crux of what graphical models or generative models or all of these things are. And it'll hopefully become a little bit more concrete later on in the course, or in the lecture. I'll give some more examples, but that's the idea of these graphical models. And in that vein, sort of one of the first types of graphical models people might hear about are things called Bayesian networks. So a Bayesian network, and I won't sort of worry about the definitions here too much because ultimately these are kind of one class of models that is often talked about in data science and AI, but they're really just kind of one class. They are defined by two things. A directed acyclic graph, G. So G is a graph over all the variables. So if I have 3 variables, say, 2, x3, I have a graph over these variables. So say I have this graph, where this is not a very useful distribution, by the way, but I'll get to that in a second. I have a graph over all the variables which is a directed acyclic graph. So it's directed, the edges are directed, and it's acyclic, meaning there are no cycles in this graph. And these graphs encode distributions over these random variables here. And in particular, the way you specify a Bayesian network is that you give the distribution of each variable xi given its parents. And this defines a joint distribution over all the variables. Specifically, the distribution it defines is just actually the product of all the I. The product of all these things from I equals 1 to say n of xi given its parents. And I won't belabor this point, but this is actually not that trivial to show. Well, for Bayesian networks, it's actually not that hard to show. But anyway, this point, I don't want to emphasize it too much here, but this condition here, this definition here is actually equivalent to the fact that each xi is conditionally independent from all the things that are not descendants of it, given its parents. So you may have seen that before. If not, I think this is the main thing to think about. And actually, this framework will, I think, become much more clear when we start talking about examples, and particularly when we start talking about generative models. Because generative models, though they aren't often framed like this, actually actually have this same kind of property here. So let's take one example. I think this is best covered by an example. Here's an example of a Bayesian network. So there's 4 nodes in a chain here. I have all this space. I should be using more space here. There's 4 nodes in a chain here, and the graph is a chain graph. X1 is the parent of X2, X2 is the parent of X3, X3 is the parent of X4. Now, what the Bayesian network assumptions let us do is that they let us specify this distribution or simplify this distribution. So if I want to sort of explicitly write the distribution, given this graph, if I want to write the distribution of all the variables here, I can transform that, first of all, just by the chain rule. So this first statement here is true no matter what the form of x is. It's that this thing is equal to, right, just like the probability of x1 and x2 is equal to probability of x1 given x2. So, well, whatever, it doesn't really matter. Probability of x2. So I can always do this. This is just the definition of conditional probability here. I can apply the same thing kind of sequentially and get the following representation. So this is going to be equal to sorry, I should make a habit of using little p's here still. P of x1, P x2 given x1, P x3 given x1, x2, and P x4 given x1, x2, and x3. Right? And that's true. That's just the definition of conditional probability. That's true no matter what the distribution is. Right? For any distribution, that statement holds. And now we're going to use the Bayesian network independence assumption and say that because we know that x3 is independent of all the nodes, of all its non-descendants, so of all nodes that came before it in the network, given just as parents, this term here simplifies to just P of x3 given x2. And similarly, this, we know x4 is independent of all its non-descendants given its parents. In this case, its parent is just x3. And so this term here simplifies to P x4 given x3. Right? Yeah? Yeah, so the question was, this assumption is not about the data. Right, I'm not talking about data at all yet. I'm talking about random variables and the distribution of random variables. We'll get to data later. Data doesn't enter in at all here. This is more like when we had that lecture on probability, and we just started talking about Gaussian random variables or Bernoulli random variables, right? These are just random variables, and we'll talk about data later. Data will enter in as observations of what value these variables take on, and that will inform how we actually do a lot of these inference techniques. But right now, we're not talking about data at all yet. So the question is, are we doing this to make computation easier? And yes, we are, but we're also, I think this might get at this a little bit more in the next slides. We're also really implying kind of a structure to the data. And that could be for computational reasons, but it could also be for reasons that we genuinely think these independencies might really hold, and we want to exploit that in actually building our models. And then if you just sort of do some counting now, right? So if we represent this distribution entirely for every possible setting for these things, we would need 15 parameters. So 2 to the 4 minus 1. On the other hand, though, if we look at this distribution, well, for P of x1, we need just one parameter, right? We just need the probability that that's equal to, I'm assuming all binary here for now, I should add, though we will quickly dispense with that assumption. We need 2 parameters to model P of x1, x2 given x1. These are all uppercase letters, so I'm talking about sort of general distributions here. I specify the that this is equal to 0 given this one being equal to 0, and the probability that that's equal to 0 given that one being equal to 1. And then the converse gives you the probability it's equal to 1. So I need 2 parameters for that. And so for the whole entirety here, I need 7 parameters to describe this whole distribution. And as you, of course, can imagine, this thing is going to grow linearly. If I have a long, long chain, right, this will grow exponentially in the number of elements I have, whereas this one will only grow linearly. I only need 2 more parameters every time I add a new variable in the chain. And so the computational and sort of memory savings of this technique are substantial here. So that's the computational reason, but I think it doesn't quite get at the heart of what's really, or maybe I shouldn't say what's really happening here, but it only sort of provides one perspective on kind of what's happening here. So the other perspective I want to offer here is what's called the generative, what I would call the generative model interpretation of this. And I think that these are actually oftentimes much easier to understand. And they are, in fact, how we oftentimes write a lot of these graphical models. We don't write them as the networks. We actually write them in terms of what's called a generative model. And the way to think of a generative model is kind of as a story for how the data is generated. Okay, so I actually kind of want to emphasize that element of a story because it's sort of kind of crucial to how you can interpret these things. So if you think of the generative model story of this network here, what you may say is that the first thing we do is we take, x1 has no parents. That just means that we're just going to sample it arbitrarily from its distribution. So we can have some parameter. So here my parameters are all going to be denoted by phi. So again, phi here is going to be a number between 0 and 1. It's the probability in that first case that x1 is equal to 1, say. So I'm going to sample x1 from Bernoulli distribution given or using this parameter phi superscript 1. Once I have my value for x1, I'm going to sample my value of x2 given this set value of x1. Right? And that comes from another Bernoulli distribution with parameter phi sub superscript 2. But importantly, there really are 2 parameters here. There's one parameter phi 2, 0. And that's the probability that x2 equals 1 given that x1 equals 0. So if I sampled x0 from my previous, so if I sampled 0 for x1. And there's also going to be phi 2, 1, which is similar to the probability that x2 equals 1, given x1 being equal to 1. And those are the parameters of my distribution. Of course, if I have more of these, those are exactly the 7 parameters that I mentioned, or 7 parameters I mentioned before. So, and the way I'm going to write that is that x1, little x1, takes on the value 0 or 1. So I'm going to write this Bernoulli distribution as being a phi 2 subscript x1. That means you take whatever the value x1 is and you just plug it in there. That gives you your parameter that you follow. And then I do the same thing. Now I know my values for x1 and x2. So I'm going to sample my value of x3. I now know my values of x3. So I'm going to sample my value of x4. And this is, of course, maybe what you first thought of when you saw that graph. But it's important to know that this is actually kind of a different thing. This is saying that we actually have a procedure that kind of causally generates this data, whereas what a Bayesian network really says is just here are some conditional independencies that the data follows, not necessarily the fact that it has to be generated sequentially like that. So there are subtle differences here, but I would actually rather you sort of build this intuition of these generative models than build the intuition of the Bayesian network in terms of conditional independence properties, because that one's a little bit more opaque. These sort of stories of how you sample variables are very easy, and they're also very easy to code too, right? We could really easily write code that would generate samples from this distribution here. So that's what I'm calling the generative model story. And this is an extremely powerful notion in really all of data science, but all of machine learning and all of statistics really as well. And in fact, we've already seen this in a few ways. So I didn't frame it as such, though actually you've already seen plenty of these generative models already in class. So for example, naive Bayes is a generative model, right? The story of naive Bayes is that I first sample my class, Y, from a Bernoulli with some parameter phi, right? That's the first thing I do. And then I sample, and I'm assuming, here we're talking maybe about categorical, so discrete valued x's and binary y's. But once I've done this, I then sample each of my xi's given y. I sample these from a categorical distribution with some parameter here, and I think, was I right? I wrote phi, yeah, I, y. So basically, every variable has an independent set of probabilities there, and I sample that 1 for y being equal to 0, 1 for y being equal to 1, and I sample each of my features independently given that, given that parameter, or using that parameter. And that really, that's, we talked about naive Bayes as being the assumption that the variables were conditionally independent given y, but really this is kind of the story about how data may come about that actually obeys that property, right? The way it comes about is that you first sample the y, and then I sample these things, independently given that y, right? So that's the story of the naive Bayes model. And the graphical model, if you want to sort of think about it, I won't write the graphical models for all these forms, but the graphical model would be that your y is your parent here, and then you have a bunch of the x1, x2, all the way to xn. That would be kind of the story. That would be the Bayesian network representation of my naive Bayes model. We've also seen it, for example, in Gaussian mixture models. So the story of a Gaussian mixture model is that I first sample z, my hidden variable, from a categorical variable. So that's has some probability of being chosen in any one of k different clusters, say. And then once I've chosen my cluster, I sample my x from a normal distribution according to that cluster. So that's the story of how data is generated according to a Gaussian mixture model. Any questions so far? Okay, so now we can start getting pretty general here. So this notion of kind of building a story is a really powerful one, because you're not, these are pretty simple, right? We're talking about, everything being Gaussian, and you basically, select which Gaussian you want. You select, which in naive Bayes, you select which of two different categorical parameters you use for each variable, depending on y. But it's kind of simple. But there's nothing preventing us from getting kind of as complex as we want. We can kind of think of these things as being arbitrary sort of blocks of code that can run that depend on all the variables beforehand and generate some random variable themselves, right? So I'll give a few more examples. Don't worry about the last one. If you've seen it, if you've heard of it before, I'm just putting it there to emphasize that this is also just a generative model, but don't worry about this one. So ignore this one for the time being. But actually, linear regression, it's a very simple graphical model, but it actually is a graphical model too. Our linear regression, if you remember, that was equivalent to assuming that you were observing the outputs as a linear function of the inputs plus some Gaussian noise. So the graphical model there would just be a model on y given x being normal with mean theta transpose y and covariance sigma squared. Now, the important thing to note there is that we're not positing any distribution over the x's. So linear regression does not assume some distribution over the x. It just assumes distribution over the y given the x. But in that context, it is also actually a perfectly valid, if very simple, generative model. Here's a little bit more complex one. Here's something called, which we'll come back to later actually, called change point detection. And this model encodes the following thing. So what it encodes, let's see, all right, I'll just use here. What it encodes is data along the 0, 1 interval where up into a certain point, it has one distribution. So here's my 0, 1 interval, 0, 1. And up into a certain point, say this point t, I have one mean. So and the variance I think is the same for both of them in this model, but you could change that too. So it has one mean. So maybe my points here look like that, and then up here they look like this. So it has a different mean, mu2, and then mu1 before this point, and mu2 after this point. So it's also important in all this kind of think about what are the parameters of these models. I didn't really actually mention this before, but in the previous ones, for example, the parameters of this distribution here would be the phi variables. The parameters here would be phi and all the mu and all the sigma variables. Here, the parameters for linear regression would be the theta variable and the sigma squared variable. And in change point detection, or change point model, say, the parameters would be, well, it's mu1, mu2, sigma, and then this t variable is also a parameter, right? The t variable determines where we do it. And right now I'm treating those all sort of as just parameters that we might estimate later, as we have done, say, with maximum likelihood estimation. I'll offer one more thing. So this is a model which I don't want you to worry about too much. But if you've seen it before, a very popular way of analyzing documents and clustering documents is something called latent Dirichlet allocation. It's a very fancy name. But it's just a four-line generative model for describing data. Don't worry about what Dirichlet distributions are. They are essentially distributions where you can sample that are themselves distributions over the probability simplex. So you can sample actually parameters which act like the phis for a categorical distribution. So any sample from a Dirichlet is going to be all positive and sum to 1. So you sample essentially topic distributions per document. So I have some number of documents, some number of topics, and then a bunch of words per document. I sample, and according to latent Dirichlet allocation, I first sample a bunch of topics for each document. I sample a bunch of words that can occur per topic, and then in a document, for each word, I sample which topic is going to belong to according to this theta that I've already sampled there, and then I sample the actual word according to a categorical distribution depending on this guy here. So again, the actual details there are completely unimportant. Unless you really want to learn about LDA, then go off and read about it. I won't talk about it much more here. The point that I want to make, though, is that this is actually a fairly, this is now, 2003 was the paper, so this is now, quite almost standard at this point. It's 13 years old now, but it's a very powerful model that's very, very heavily used in natural language processing, and it's described by essentially a four-line generative model. And here I should add that the parameters here would be alpha and beta, though we'll get to what parameters mean in settings like this in a second. Okay, so that's hopefully gives a brief introduction to kind of what I mean by these generative models. The reality is they're actually quite easy to understand. They're very intuitive because it's sort of, they read like computational procedures, right? They read like ordered things. First I generate this, then given that I generate this. They're very much just code essentially, just with random variables instead of deterministic variables. And in fact, this is exactly what we're going to exploit when we talk about probabilistic programming. So probabilistic programming essentially is an effort to make writing those things just a matter of writing code that looks like that. And that's what you'll probably want to use mostly in data science, not all the crazy math that's been developed for these things. So let's talk about inference now. Inference is sort of one of the major challenges and questions when it comes to graphical models. And inference is really actually a very easy problem. The problem is, if I observe some elements of my data, or actually, you could actually even do it if you don't observe anything and you just want to know the probability of some other things. But in general, we're going to think about inference when I observe some variables. So if I observe the value of some variables here, so say I have this chain here, and I observe what value x1 is. It takes on the value 0, say. Then inference is the problem of inferring what the distribution is over the remaining variables, right? Over the variables that you did not observe. Because it's no longer the same as the distribution, the joint distribution over all the variables, right? I've essentially frozen some, and so the remaining variables will have a different distribution from what they had originally. That's the crux of inference, is I want to infer what the distribution is over the remaining variables, given the fact that I've observed some of them. There are also twists on this called things like marginal inference, where I only want to know, the marginal distribution of one variable. I don't care about the joint distribution of all the hidden ones. I just want to know what's the distribution of one. But I'm going to mainly kind of sweep those things all under the rug and talk about inference really as trying to come up with the distribution over the unknown variables given what we've observed. And in fact, we've already done this with, for example, naive Bayes, or with, for example, Gaussian mixture models and the EM algorithm. We've already done this, so I'm going to try to emphasize that as well. OK, so let's talk about how we might go about doing this, right? For our graphical models, we assume we have one of these generative model stories for them. So we assume that we have some story that says, first you make x1, then I generate x2 given the value of x1, then I generate x3 given the value of x2, and then generate the value of x4 given, et cetera. So the inference task, at least from a qualitative standpoint, this is sort of very kind of qualitative here, but it seems kind of easy if, for example, we were to observe the first variable in this chain, right? Because our story said, well, first I generate x1, then I'm going to generate x2 based upon x1. So the only change in my distribution is that I fix x1, and then I use that value to generate x2 rather than kind of a placeholder for x1, right? I actually use the actual value that x1 takes on to generate x2, but then I have sort of the same story. I can easily create a new generative model, for example, that would directly describe the remainder of the chain if I knew x2. Okay, so in some sense, people first see inference, and it seems kind of easy because I could just, I can easily generate a new generative model from that. Or shouldn't use the word generate twice there. I can build a new generative model, just basically, having x1 be fixed. But that is not always the case. So think of the other situation now, where I observe x4. Okay? So before I had a graphical model or a generative model that sort of said, first I make x1, then I make x2, then x3, x4. But now I'm saying, oh, and by the way, x4 equals 0. What is my resulting distribution over the first 3 variables there? And that is not an easy problem, right? You may be able to use Bayes' rule to figure it out, and you can, in fact, here. You actually can also do something called variable elimination here. But it's not actually an easy problem in general. And I'll quickly get some examples exactly why this is quite a hard problem, in fact. But it's not, the point I want to make is that if I observe this variable, I can't easily write a generative model story that describes what value these variables take on, right? Because, for example, if this variable can only take on value 1, say, when this one is 0. Just say that's whatever those variables are. I specify it such that if this one is 1, this can only take on value 0. That is actually a tricky thing to encode, right? Because I can't use my prior, or I don't want to use the word prior because I'm going to use this later, but I can't use my existing generative model at all, really, because it says, you sample this with 0, 1 with some probability, but I know from knowing this guy that this has to take on the value 0, say. So it's not easy, is all the point I want to make right now. It seems, these two things may seem kind of similar, but this one, you no longer have a way of drawing a graphical model that would actually, or a generative model that would actually capture that very well. You can, again, but not easily. It's not immediately obvious how you do it. And this is the problem of inference. So usually when we talk about inference, you very rarely care about this problem. You talk about this problem. So for example, we already did this, right? We already did a naive Bayes, for instance. We said, OK, this is my graphical model, and I observe these things. right? I observe the x's. Those are not the first element in my graphical model. They are children elements. And my question was, what's the distribution over y given those? That actually was an inference problem, right? We were saying I observe these things, and usually we shade things in when we observe it. So in naive days, when we had a new example, we would say I'm observing my x1 through xn variables, and I want to determine the probability of y. Now we did that using Bayes' rule, and we sort of did it by hand, but we couldn't easily write a generative model like that would describe it. We have to then have to actually use Bayes' rule to get that distribution. The same thing, exact thing we did, for example, with Gaussian mixture models. We inferred the probability of the distribution over the hidden variable given what we've seen so far. So anyway, let's talk about a few ways you can do inference, because there are a handful of ways. And typically they break down into 3 approaches. There are other things you can do as well, but these are the 3 most common. So on the one hand, there are exact approaches. So these include things like a direct application of Bayes' rule, but also more sophisticated techniques, which we're not going to cover, called variable elimination methods. You can essentially exploit the structure of the graph to remove variables and simplify your graph if you only know certain things or only care about certain elements there. And you can actually sometimes perform inference using these variable elimination methods. But for reasons I will show you in a second, these often are just not tractable. So it turns out that actually exact methods, even when the original distribution is compact, so it has a small number of parameters, everything seems nice, it actually can sometimes still be exponentially hard to solve inference exactly in a graphical model, and I'll show an example of that in a second. And so because of this, there are actually 2 other approaches people often take. And these are sort of big buckets here. And again, the goal of this class is not to cover these things. I'm going to largely wave my hands over how they actually work. But you should at least know about these approaches. And so when people mention them to you about ways to solve these things, they should kind of ring some bell. And so the first approach are what are called variational approaches. And maybe I should put this approach second, because they're a little more complex than the third one. But variational approaches essentially say it could be hard to exactly represent the distribution over the hidden unknown variables given the observations. 4 things we'll see in a second, that can be a very hard problem. So what we're going to do instead is we're going to assume some other simpler distribution over the hidden variables. And we're going to try to fit that distribution as well as we can to the true distribution. And that's the nature of all variational approaches. The second approach, or third approach, I guess here, which is the one we're actually going to talk about. This one we'll mention no more variational approaches. Though I should add, they are oftentimes the most efficient ways of doing things. So if you want to solve LDA, latent retrieval allocation, for example, you should use a variational approach. You should not use sampling methods, I think, usually at least. They often work very well, but they are actually quite mathematically complex, and I don't think they actually really belong. Again, I love talking about them, so I'll be happy to, just like I like talking about backprop, but I'm not going to cover them in this course really at all. The approach we're going to talk about a little bit, just because it's what a lot of the tools you might use are sampling approaches. And in these approaches, we have a little bit different of an objective. What we're going to say is we're not really going to try to describe the distribution of the hidden variables, in a closed form or in a sort of exact manner. What we're going to do instead is just come up with a procedure that will draw samples from these distributions. So we were going to kind of describe the distribution implicitly by being able to draw samples from it. And it turns out, actually, oftentimes, that's sufficient for what you really want to do, right? If you want to get some notion of some elements of the distribution, say their mean or your variance, you just draw a bunch of samples and then look at them, right? Look at their shape, look at their histogram. If you want to do like an EM-style algorithm, a learning algorithm, you can actually, we talked about computing exact expectations, so that was actually exact inference. But you can do the same thing if you just have a few samples from your model. You essentially use those samples and just train the model as if, on those samples, you knew what the value of the hidden variables are. And that is works just as well, essentially, as EM does when you can't, or when it's difficult at least, to create an exact distribution over the hidden variables. So oftentimes, for a lot of things, samples are perfectly sufficient. And in that case, these approaches are very compelling because they let us draw samples in cases where this one might be very hard for mathematical reasons, and the first one might just be very, just completely impossible to actually do. All right, any questions? Okay. So let me talk about one case of exact inference, and I won't even write it here because it's sort of the case we've already done. So this is the Gaussian mixture model, and I just want to emphasize again that you've already actually done inference. So in the Gaussian mixture model, we assume that the generative story was that we sample z according to some categorical variable, and then given the setting of that, that's kind of like the cluster indicator, and then given that setting, we sample x from a normal distribution with some mean and some covariance. And the expectation step of the EM algorithm was just really an inference problem. We were trying to compute the probability of our hidden variable given the known observed values of x, right? So for a given x, what is its and assuming in that step, we assumed that the parameters were known. So we assumed that we knew phi and that we knew mu and sigma. What's the distribution over our hidden variable z? That was the question of the Gaussian mixture model. And the way we did that was we just did it through Bayes' rule, right? So we don't have this thing in our generative model, but we do have the opposite one. We have this one, right? That's specified by our generative model there. We have this one. That's our categorical variable. And then, because z here is discrete, we can sum over all possible values of z pretty easily and come up with a distribution over the possible values of z. And that is our E step. So our E step really was performing exact inference over z given the x's. And so now I want to highlight just exactly why we need, though, to use approximate inference sometimes. So here's another graphical model. It looks like naive Bayes, but it's actually very, very different because the arrows go the other direction. JT, can you let me know how far down? If I start going down below this thing, let me know. If I go below the line, I can draw on here. I'm good. Okay. So consider the following model. So we have zi. We have a bunch of zi's, and each zi is Bernoulli with some parameter phi I. And then we observe a variable x that is normal with mean some parameter times the z's. So some some sum of all z's weighted somehow with some parameter, and then sigma. So essentially, each of these are 0 or 1. You take the ones that are 1, you add up those elements of theta, add a little bit of noise to that, and that gives you your x variable. Does that make sense to everyone? What that generative model story is? We say that we generate a bunch of those randomly, then we add them up, take some weighted sum of them, and add, and that's the mean of a normal random variable. So now, that's sort of a very nice compact distribution, right? It only requires n plus 1 parameter, or I guess 2n plus 1 parameters, right? The phis, the thetas, and sigma 1, or sigma squared. So it's a very nice distribution. But now suppose that I observe x. So I observe what that sum is. And I want to come up with my distribution over the z's given the x. All right. So this is actually, among other terms, it's called a packing problem. So you have to figure out some number of these things that I can add up according to those parameters theta to give me something close to what I've observed here. And this is a combinatorially hard problem. So it's actually very hard to even find, what's the most likely set of z's that led to this. And I will just tell you, there is no way to represent this distribution over the z's other than having a separate probability for each one. So I have to actually use Bayes' rule still, right? I have to use Bayes' rule. I say that the probability of z, where's z? probability of z given x is just equal to the probability of x given z, p z over the sum over all z, p x given z, p z. The problem here is that this sum now is over 2 to the n possible assignments. And I can't actually do this other than just computing all those 2 to the n possible assignments. That's the only way I can actually come up with that distribution. So clearly, for a large enough n here, this will not work. And we cannot actually do exact inference in this domain. Questions there? So this motivates other approaches, and the one that kind of motivates are these sampling-based approaches. So rather, instead of trying to describe the distribution exactly, maybe I can just draw samples from that distribution. That may be easier or harder depending on the precise character of the distribution, but maybe I can do that. And so a naive strategy, this has been called rejection sampling, is that look, I know I have my generative model. I have a way of generating random samples from my distribution. Let me just generate random samples until I find one that is consistent with my observations, right? So if I have this chain, right, I can just generate random variables according to this chain. And if my observation here was x4 is 0, I just throw away everything where x4 is not 0. And the remaining samples are guaranteed to be samples from the distribution over these guys, over the remaining variables, right? So that seems kind of nice. That seems reasonable. The problem, of course, is that this is just sort of sweeping the problem under the rug, because if you have a large set of observations that is maybe low probability, the chance of just generating your observations you see kind of randomly is very small. So if you observe this being 0, but the probability of getting a 0 is very small, you have to generate a lot of samples before you have enough that actually fit your observations. And in the case of continuous random variables, it's even harder, because then you may actually have, depending on your distribution, it can be very hard to do, and you can have 0 probability of ever actually generating the variables that you see. You can do something else with continuous random variables, but it has all the same problems as this. So this is kind of the first thing you could think about in sample-based inference, but it's not what you actually want to do. And so what you actually want to do are a class of methods called Markov chain Monte Carlo methods. And here I have one slide on this. I am not going to go into detail about what these things are. But what these methods are is that they are actually, instead of trying to kind of one-off generate samples from our distribution, right, where we sort of say, OK, I'm going to just generate a random sample and check if it's consistent with my observations, what these do is that these actually maintain a setting of all the variables and iteratively update these variables according to some scheme, such that as you proceed further and further, as you execute these things longer and longer, they actually start to approach samples from the real distribution, the actual distribution you care about, the posterior of the hidden variables given the observed values. The name MCMC, Markov chain Monte Carlo, comes from the fact that you can view the generating process of these big things as a Markov chain, but there I'm not going to really dwell on that because I don't think it's actually that useful to understand the algorithms. Plus, we have, I'm describing this all in one slide, so I'm not going to cover it in sufficient detail anyway. And so the way these things work, all of them, though, is that they basically, prescribe a set of values to all your variables, and then I iteratively update those set of values by sampling certain elements given other elements. So the most famous, or one of the most famous cases of, there are really two actually famous cases, of Markov chain Monte Carlo are called Gibbs sampling and Metropolis, or Metropolis hasting, though no one ever does the hasting modification, so I just call it Metropolis sampling usually. So what these are essentially schemes of how we update our variables in the set that we're maintaining that are valid, and that they will give an actual convergence to the true distribution and generate samples from the true distribution as you go along. So in Gibbs sampling, what you do is you basically take your variables and you iterate the following over all the hidden variables I. For each hidden variable I, I'm going to consider that variable being free. I'm going to fix all my other variables. I'm going to fix both the observed ones, x's, and all my other hidden variables. And I'm going to sample zi according to the distribution that is implied by my generative model. Now, that's not always possible to do. And that's why you might use something else. But you can actually do it oftentimes. So for example, in this case, right, I actually can come up with pretty easy with a distribution for, if I assume everything but one z is fixed, I can easily come up with a distribution for what my that probability is, because now the z is only over, I'm summing only over one term in the denominator here, and so I actually can quite easily come up with a with a way of sampling that zi, assuming x is fixed and assuming all the other zi's are fixed, all the other zij's, where j is not equal to I, are fixed. Okay. So that's the idea of Gibbs sampling, is that you basically fix all but one of your random variables and then sample that one given all the others being fixed, and you iterate over all the variables for a long, long time. That's called Gibbs sampling. Metropolis, or Metropolis Hastings, is actually a more complex thing, which I'm not going to describe at all here. This is the math if you care about it. Basically, this comes in handy when even that distribution of the probability of this one here is one that you can't even sample from efficiently. You can't come up with a closed form for even that one. This happens a lot of times for when you have continuous random variables, for example. And in that case, you actually have to sample from some other distribution called Q. And basically, Q gives a distribution of a new possible point given the old existing value of z. And then you can either accept or reject that proposal given some ratio here. So it's a one. It would take a whole class to describe this well, so I'm not going to do that. But that's sort of the basic principle: is you want to sample from that, but you can't. So you sample from some other distribution Q, and then you may or may not accept that distribution. It's actually very related to rejection sampling, but I'm going to throw my hands up at this point and say, if you want to know more, you should take a probabilistic graphical models course. Any questions besides the obvious many ones you may have? Yeah.
Like the NLP notebook where we were sampling.
Yeah.
You sampling, you fix one word from your thing and then you iterate on the possibilities of that.
Yeah. So the question was, how does the sampling kind of relate to the sampling we did in our NLP notebook? So yeah. So essentially, if you want to do something like Gibbs sampling, what you would do is you would fix all but one word and sample that word given all the other words. What you actually did though was you sampled sequentially, right? You would always sample the next word given the previous one, and that was much more just like a normal generative model, right? It was saying, here's my generative model. My story is that I have a distribution of my next word given my previous word, so I'm going to sample from that distribution, and I'm going to sort of create according to that, and that was much more a generative model. If you do Gibbs sampling on those, you would have a fixed text of a fixed length, and you would basically then have to use both the subsequent word and the previous words, because those would both relate to the probability of the current word, right? If you had n grams, then all n terms afterwards would also depend on that term. So you would have to actually include all those things in your probability, and that could get difficult, and so that's why you don't usually see that. You usually just see sequential sampling for the NLP notebooks, or for those kind of n-gram models. But you could do this. You could, and maybe you would get better text. But we have a generative model for that, so we don't really care too much about that. It would be good, for example, if you saw some text and wanted to fill in missing words. That would be a good use for something like Gibbs sampling, right? Where you didn't know what you had a whole document, but one word was missing. Then you could use Gibbs sampling, very nice, or maybe a couple words were missing. You could then use Gibbs sampling to sort of sample what that word should or could be, given everything else you've seen. But it would require some carefulness there, because you have to consider both the probability of future words given that word and the probability of that word given past words. You have to consider those both. Okay, so in the little time I have left, and I might not get to the example too much, but hopefully I will. I want to talk a little bit about Bayesian modeling. So the crux of Bayesian modeling, at least in the, again, 20 minutes I'm going to not give it due credit here, is that so far in class, we have made this very hard distinction between parameters and random variables. So, I would always write things like the probability of the theta given these parameters. And I used a semicolon to kind of indicate this was, the things that lived right at a semicolon were parameters, other things are variables. So, when I say that y is a Bernoulli random variable here, this is a random variable. It can take on any quantity. But this phi here is a parameter. It has one value. We don't think of it being itself a random quantity. We think of it as just having a value. And the whole idea of, say, maximum likelihood estimation, is that we would try to find, a single setting of the parameters, right? A single value for the parameters that would make the data as likely as possible when generated from those parameters, the distribution parameterized by those parameters. This is kind of the crux of almost all the statistics work that we did so far. So I want to at least very briefly offer an alternative where instead of these things kind of being just parameters, we actually think of what we were calling before parameters as themselves potentially being random variables. So I'm going to do the following. I'm going to say, instead of writing things like p of x parameterized by theta, meaning that we have some fixed parameters and we generate a probability over x given those fixed parameters, I'm going to write things like this, like probability of x given theta. And what the implication here actually is that theta itself, the things we were calling parameters before, I'll just keep calling them parameters, but they're a little different. These parameters themselves actually also have distributions to them. Right? So they also actually have a distribution. And this is the crux of what's called Bayesian statistics. We don't try to find a single estimate of what one value that theta can be. What we say instead is, I don't really know what value theta is going to take on. I can't know that because I've only seen a sample of data. I don't know what value theta should take on. And so I'm going to instead represent a distribution over theta. Okay. Now, in order to do this effectively, you need to also have what's called a prior on theta. So I need to have a distribution of what my data should look like given my random variable. But I also need to have some notion of, that in itself now, if this is a random variable, it has to have some probability as well. And so I need to specify what's called a prior probability of theta. And here, I'm again going to say parameterized by alpha, where alpha here are what are called hyperparameters. And those things are just, those are actually parameters again. Those are things that we're not going to try to have a distribution over. But in fact, those things we will very rarely ever change. We'll just fix a value for our hyperparameters like 1, and then assume we kind of are good from there. So this is sort of I should also say that there's much more arguments that Bayesians and frequentists get into than just this. From a practical standpoint, this is kind of what you see. When you talk about doing Bayesian statistics, you should really think about always maintaining a distribution over your parameters, not just over the random variables that you have. And so I guess the computational crux of Bayesian statistics is that we want to typically compute, so that this distribution here gives us a prior over our parameters. The most common operation in statistics, in Bayesian statistics, is to compute what's called a posterior over our parameters. So that says, if I've seen some data generated from my distribution, right, what is my new distribution over theta? Right? So I have a prior distribution. That's kind of what I think the values I think it'll take on regardless. According to my generative model, I have theta here. It generates some data x. If I observe x, what I really want to characterize then is what is my theta given some observations x? What's the probability of theta given those observations? And we can write Bayes' rule here. We can say that this thing is equal to, this is equal to the probability of x given theta. This is the same as we did before, times the probability of theta. And that has these hyperparameters here. Over, the sum, but oftentimes theta is continuous, so it really is kind of an integral. And the integral of P of x given theta. P, I should probably say theta prime here, because this is the variable I'm integrating over. D theta prime, alpha, d theta prime. So that, this computation here is actually the crux of Bayesian statistics. I want to say, what is my distribution over my parameters given the data I've observed? And so now everything is kind of moving towards this notion of inference, right? We no longer talk really about maximization. We don't talk about finding a single setting of our parameters that maximizes the probability of the data. We say instead, given the data, what is my distribution over my random variable theta? And that's kind of the Bayesian way of doing things. And in some cases, I mean, a lot of cases, right, as you may imagine, this term down here is really hard to compute. The top term is fine. The top term, this is the first term we have in our, this is, the probabilistic model of x. This term is our prior. We can compute those fine. This term is really hard, though, because that term involves an integral over theta. Theta could be continuous valued, and oftentimes there's just no way to actually compute that in closed form. So that's sort of the hard part of Bayesian statistics, is that it's oftentimes very hard to come up with a distribution here. And so we're going to resort oftentimes to sampling, because now they're all random variables. We can just think of it like an inference problem. So let's just draw samples of what theta should be. Before I get to that, though, I want to mention that there are a few cases where you actually can compute the exact distribution over theta given some observed data. So for example, there's a technique called Bayesian linear regression, which posits a normal distribution over theta. So theta itself has a normal distribution with, say, mean 0 and covariance some number times I, times the density. So it's assumed to be a bunch of independent random variables is the prior we have on theta. And then the probability of y, some data given theta and x we don't try to model here explicitly, but y given theta and x is normal with mean x theta transpose x and parameter sigma squared. And I'm going to tell you without any proof here, but I'm going to claim that in this setting, if you have those things and you write down, the distribution of your theta parameters given x, you will actually get another normal distribution. So it turns out that your distribution over theta will also be a normal distribution, with the mean and variance given by that. The variance looks very much like the covariance of the data, just with an additional term here. And the mean looks very much like the least squares mean. You just might have an additional term because this term has the I there. So the point here is actually not how you derive this, because it takes some work to derive this, I should say. This is not meant to be obvious. This is meant to be actually quite opaque. But the point here is that this is one situation where I'm just telling you without any real proof that when you assume a Gaussian prior to theta, and you assume that your data, your observational distribution is Gaussian given your parameters theta, then your posterior over theta, the distribution of theta given the data, is also Gaussian. Which is pretty impressive, actually. It's surprising that works. And you can prove it by actually just plugging in the Gaussian distribution into that. But I mean, you have to do things like integrate over things, so it gets kind of gross and kind of annoying.
But that would be only true if the x's also are normal.
So the question was, does it assume x's are also normal? No, it assumes no information about the x's at all. So x's can have any distribution they want. This is saying, yes, that's a good point. So x's can actually have any distribution they want. No assumptions on x's, just an assumption on y given theta and x and theta. Yeah?
So in naive case, like the concept of prior makes sense because it's just the distribution of the labels, right?
Yep.
So in linear regression, how would you interpret prior?
Yeah, so great. So what does this mean to think of a prior over theta? So again, I think the best way of thinking about it is as a generative model story. So the story for this model is to say, okay, I'm going to sort of sample from all possible regression tasks here, right? So I'm going to sample theta, first of all. So I'm going to sample some random set of parameters from, say, an independent Gaussian normal distribution. And then, once I sample those, I'm going to sample my y's, and I see some x's. I'm not going to try to model those, but I see some x's. I'm going to then sample my y's also from my Gaussian distribution, where I take theta, multiply it by x, add some noise, and that becomes my y's. Okay, so that's kind of the generative story. Now that seems crazy, right? You don't think of data being generated that way, but if you sort of think of maybe the universe of all possible linear regression problems, maybe that is reasonable, right? Maybe your parameters, in general, kind of tend to have not too big coefficients. They tend to be, oftentimes be a little closer to 0 than really, really far away. And so you have some notion that, your parameters, maybe your theta parameters should be kind of, maybe all things being equal, they should be closer to 0 than anywhere else. And so this is the biggest, I think, criticism of Bayesian statistics as a whole, is that it depends too much on these priors that aren't necessarily that useful. They're kind of arbitrary, right? But on the other hand, it does kind of give you a very clear way of saying, well, if you don't think that's true, then just give me another distribution. It could be anything else, actually. It could be it could have some mean there in the normal distribution. It could have some other variance. Tell me what the distribution should be over my hidden variables, such that over my parameters, which are hidden variables here, such that you think the task makes sense. So you're free to choose whatever prior you want. I'm choosing that prior. These are often called sometimes uninformative priors if the prior doesn't really encode any real information. But you choose whatever prior you want, and then from that I can give you a distribution over what the parameters are likely to be.
I guess this would be useful if you're building a model over time and you want to update your data, right?
Yeah, I won't worry too much about over time, because yes, you could use a prior of the previous theta with some. You can do that, certainly. I'm not going to worry too much about that. That deals with now things like random walks and stuff like that, and Brownian motion, which I'm not going to deal with. But you could do that, absolutely. But I'm just thinking of it in terms of a static case. What's my theta? Well, maybe a little bit more likely to be 0 than anything else. But by making that variance big enough, so rho becomes really big, say, I could make that fairly fairly wide, right? Doesn't really matter. I think there's actually I think there actually might be a typo here. I think one of these rows should be an inverse there. I'll fix that in the notes. Okay, so I want to mention one term, and I'm sort of blazing through this right now, and I realize that. I just want to mention one term here, which is this notion of what's called a conjugate prior. For the most part, you will not be able to come up with this distribution here. So for the most part, you have some prior over your parameters. You have some observational distribution, given your parameters. You cannot compute the posterior of your parameters given the data. I mean, for most, by some sense of the word most, right? But there are some cases where you can, and these are called conjugate priors. Or conjugate distribution sometimes too, but conjugate priors is the term you usually hear. And actually, it turns out that the normal case we just saw was one of those, and that's why this is possible. But all this means, so I'm not going to derive these things, but all this means is that if your parameters are drawn according to some distribution f, say normal in the case we just saw, with some parameters, alpha, hyperparameters alpha, and my data is generated given my parameters are from some other distribution, then if f is what's called a conjugate prior for my data distribution g, then it turns out that my distribution of my parameters given the data will also be of the same distribution f as the prior was, just with a different set of hyperparameters. Okay, that's a long, convoluted way of saying things, but all it really means is that for certain pairs of functions, like the normal distribution, you can describe this, and in fact, the posterior distribution will have the same type of distribution as the prior. It will just have different parameters here, and that's what's called a conjugate distribution or conjugate prior. So f here is called a conjugate prior to the distribution g. When you can do those are nice. For big models, you will never have those. But for one kind of pair, like normal, like Bayesian linear regression, you can have them. If you care about the, you may have heard certain things, but you may have heard these terms before. But a normal distribution is the conjugate for the mean, actually, of a normal distribution, just for its mean. The inverse gamma distribution is actually the conjugate prior for the variance parameter of a normal distribution. If you talk about Bernoulli's or categorical variables, then the beta or Dirichlet distribution is the conjugate prior for those. So I'm not even going to say what those are. We can look them up, but those are where those things those are actually why you see things like beta distributions or Dirichlet distributions in machine learning or in data science, is because they are conjugate priors. So a little aside there. OK, so I actually don't want to dwell on that at all, because I want to try to see if I can cover one last example here, which is a simplified. The name Bayesian change point detection actually means something which is more complex than this thing, but this is a very simplified version of this. So I'm going to go back to my change point example. Right, this is this example of I have data where on the real line, so x is on the real line. Oops, I forgot to write x there. So x is the same, is uniform 0, 1. If x is less than t, then it has one mean. If it's bigger than t, it has another mean, both with variance. And that's my generating distribution here. And in the Bayesian setting, so my parameters in the sort of the classical setting that I described before, where my parameters were the two means, so it's mu1, mu2, sigma squared will also be a parameter, and then t was a parameter. So what I'm going to do in the Bayesian setting is I'm going to take those things and put distributions over those parameters as well. So now these parameters themselves have distributions over them. They have priors. And they are themselves random variables that we're going to actually come up with their distribution for. Yeah, question? Oh, I just making it a little easier. Yeah. Why do I use the same sigma squared? You don't have to. Just one less line to write. I guess I sort of cheated here. I did this fine. OK, so again, this is getting kind of complex now. But the way to think about this is as a story. So I'm going to sample some t in between 0 and 1. That becomes my change point. I'm going to sample then some mu1 and mu2 from the normal distribution. Those become my new means. I'm going to sample whatever this means, whatever this distribution looks like. But you can look it up on Wikipedia and see what it looks like. I'm going to sample my sigma squared from an inverse gamma distribution. And that becomes my new variance. And then I sample a bunch of x's from the uniform. And for each of them, y, given that x, is either normal with mean mu1 or normal with mean mu2, depending on which side of the line it falls on. So in the very little time we have left, let's see. So that's sort of a nice story for a generative model, right? It's kind of complex, but you can kind of imagine what's happening here. So let's see what this looks like. And I'm going to do it in the language of probabilistic programming. So as I said, in recent years, there's been a lot of effort to automate these things. So this is sort of a nice program. But then if I tell you, OK, I'm going to give you some data. I'm going to give you some data generated according to this, or maybe not, just some data. What's the distribution over t from this, given this data, right? What's my posterior over t? That's kind of hard. I actually don't even know if I'd be able to do that easily, without resorting to sampling methods. It's hard, right? Because this is, t involves this weird sort of distribution here about whether on what side it's on. I don't really know what the distribution of t would really look like here. So let's talk about how you might do this. So I would even have a hard time, frankly, writing code. All the MCMC code, even a Gibbs sampler would have a hard time writing, I think, to sample from this. So how do we do this instead? What we can do instead is we can write these models in a form that looks very much like the generative model we specified. And we're going to do this, and this sort of general technique is called probabilistic programming. And there's been a lot of effort and focus on this in the past 10 years or so, though it goes back much further than that as well, I should say. We're going to use what's called the PyMC framework. And one of the homework problems, though it's probably one of the harder ones, so I might not recommend if you're going to avoid one. Do it if you're interested in it, but it's going to be tricky. Is we're going to use the PyMC framework. But we're going to use the PyMC framework to talk about how we model these things. So the nice thing about PyMC is it lets us basically write these things more or less in the form that we kind of expect them to be. So T is a uniform. You have to specify both the name of the parameter and the parameter itself. So here you have the name is the first thing you pass to these constructors. So we're going to create T, a uniform variable between 0 and 1. Mu1's normal with mean mu and initial. It's actually, by default, their normal uses the inverse covariance, or inverse variance, not variance. So 0.01 is actually the inverse variance. The variance here is 10. Sorry, inverse variance squared. So the variance here is the square root of, variance is, yes, inverse variance. Standard deviation would be 1 over the square root of, or would be the square root of 10 here. Tau is gamma. Because we're specifying the inverse thing, we actually use a gamma, not an inverse gamma. This is why it's so much fun to do these things, but it's just little things you have to remember. And then now y is equal to a bunch of uniforms where they're all between 0 and 1. And sorry, x is a bunch of uniforms between 0 and 1. There's 100 of them, and y is equal to a normal distribution with mean mu1 if x1 is less than t, or mean mu2 if x1 is greater than t. And so I'm sort of multiplying these things together as you might kind of think to write this thing programmatically, right? And it has then inverse variance tau. And I create, and this is just sort of boilerplate code now, I create a model that has all these things. If I want to sample from my model, I create an MCMC sampler. You actually could just run sort of straightforward sampling here, but even there, it's just easy to use the same framework for all of this. And so I'm going to set, I'm going to create an MCMC sampler, and I'm going to draw 100 samples, which actually end up being 100 independent samples here. And so here is what, if I run this, here's what these samples look like. So I'm plotting now different instantiations of my x variables and my y variables for each different sample. So as you can imagine, this kind of looks like what you would expect, right? So I'm sampling a random t, and you can kind of tell where the breakpoints are in each of these things. I'm sampling a random mean. So the means are different. I'm sampling, not that it matters, but I'm sampling random settings of x in each case here. And then I'm sampling random settings of y for each of those, depending on the mean. So these are samples drawn from that generative model. Okay. And now the nice thing, and that you already could have written, right? You already could have written that. That's pretty easy, right? You just, as long as you have a sampling procedure for each of these distributions, which Python comes with, you could have written that. But what's harder is to say, okay, now suppose I observe some data. So suppose I observe that data. That's a collection of x's and y's that I observe. What is my distribution over my unknown parameters now? And the way you do this, and that's very hard. Now, this is now inference, right, where I have a long chain of things, and I say I observe these things way at the end. What's my distribution over the things at the beginning? And the nice thing about PyMC, or these probabilistic programming languages in general, is that this is all kind of built in. So all you do is you do the exact same thing. I'm just showing the different lines here, so the rest of the lines are the same. But instead of saying that PMs are uniform and just leaving it at that, I also say that they are actually observed variables, and they have a certain value to them. And same with the y's. Y's are observed variables, and they have a certain value. They're still random variables with this distribution, but we also say that they're observed, and then we observe them to have this value. And now I run MCMC again. Here there's a parameter called burn, which says, from the first few iterations of one of the samplers, you're going to have bad samples, so you ignore those first few ones, and then you only do it afterwards. You only take sort of the samples afterwards. But when you do that, you get samples like this. So this is now showing, again, all kind of run automatically. So you just specified the model, and you said MCMC sample a bunch of samples, and these are now showing samples over my parameters. So I've run a bunch of things, and I get a sample of parameters t that basically in this case varies between 0.44 and 0.5. And the reason it varies there is that the actual change point was 0.5, but there was a little gap on each side, so it didn't really matter where it was. So all those are equally likely according to the Bayesian model. Mu1 and mu2, well, their means actually were 1 and -1 in this data here, and there's going to be some change there depending on exactly which side you sample from, but those are the actual means you recover. And similarly, you're actually recovering a pretty good estimate of the inverse variance of your sigma distribution. So I sort of, this seems kind of easy, but I want to sort of emphasize what's happening here. We are drawing samples from the posterior over our parameters in a case where I would have been really hard pressed to come up with any way of doing that computationally. And these programming languages will actually let you. And so you'll see an example on the homework if you want to do that homework, where you basically, the inference procedure is very hard, but you can use these models, specify them in a language like this, and then use these techniques to give you an understanding of what your likely distribution over your parameters is. And this can actually act as a drop-in replacement for a lot of work we did in machine learning, where you, instead of maximizing over your parameters, you sample them using a Bayesian framework. Okay, so I did get through it barely. I guess we had some projector issues at first, but fortunately got through that. Next time we're going to meet Monday to talk about MapReduce, and I'll post a note on Piazza about the homework changes.